There we go. All right, we left off here with collecting gases. Let me get it to full screen. Okay, about halfway through the chapter here, and we've kind of done the most of the math and equations, and we'll continue to use the ideal gas law, but there's really no new gas laws. It's all just putting those to use. This next portion here where we left off is really more for your lab. So I'm not going to put one of these on the exam, but it's good for us to cover it, for you to be aware of it. So here it's saying gases are often collected by having them displace water from a container. That's because this is a cheap and easy way to do it in teaching labs. The problem with this is that that you'll cover in 162, and right, if you don't have a dryer, you hang clothes on a clothesline, and you do this because water evaporates, right? So when you collect a gas this way, there's also water vapor in that collected gas. Right, and so we're covering this here obviously because it's a gas, and we just covered and talked about the partial pressure, Dalton's law, and so you have to, when you collect these, account for the pressure of both whatever gas you're collecting and some of the water vapor. Now, the water vapor is going to be smaller because the boiling point of water is higher, which you go into in detail in Chem 162. And that's what this is foreshadowing for here. Depends on the temperature. And that's because the vapor pressure of water is different at different temperatures, which if you've ever cooked, pasta or something on the stove, and you've seen as the water heats up before it gets to a boil, you'll see the steam coming off. You can actually see it with your eye when it nears the boiling point. Right, if you collect a gas sample with a total pressure of, this is something whatever made up, it's pretty close to 1 atmosphere. The partial pressure of the water vapor, this is the standard pressure of the water vapor. Again, you'll see this number again, and use it again, but only in Chem 162. So if this is the pressure, the total pressure, you need to subtract the water vapor pressure to get the actual pressure of the gas if it was completely dry. So in more high-tech setups, you would collect it. You might have a drying tube there. But in these simple ones, which we'll see on the next, I'll just go to the next slide. This is sort of the type of setup where you'll have a test tube and some tubing, and you'll have this reaction. Some labs have already done this potentially, but you'll do this again usually in Chem 162 for redox. Anyway, it doesn't matter what the gas is that you're generating. In this instance, it's the hydrogen off the HCl, the acid, in a redox reaction, and you get H2 gas, and that's what it's collecting, right? But the water molecules have an oxygen, that's the little red sphere. And so in here, what they're trying to show you is that the gas is evolving, and it can bubble through the water, and you can trap it here, and then with markings on, whatever glass container this is. This looks like a simple beaker. Usually it's a better container, but you'd have markings here on the side, and you can keep track of the volume that comes off. But as the bubbles of hydrogen come up, they're going to take some water with them, and you have to account for that. Okay, then depending on what the temperature is of water, there's a different vapor pressure. So here's that one we saw on the slide before. Most things are done at room temp. You could potentially do them at 0, and you get these different pressures, right? And then all the way up to 100, assuming sea level, right, then that's where water boils because the vapor pressure is equal to the atmospheric pressure. So if you do some of these more, a little more challenging problems or something where you're not, at 25 degrees, you don't use the standard amount, you could come use these different amounts. But I'm not going to put one of these on the test. Here we'll do an example, but I think we have enough problems, and this is more of a lab question which I think should sort of stay in the lab portion of the class and not in the lecture. But anyway, we're here. Let's do this one. So it's telling us, there's 1.02 liters of oxygen gas collected, 293. So now we know what pressure to go back to the table at. Total pressure, find the mass. So you can see here, and this was a question before about what will be on upcoming exams, right? Here we're clearly dealing with gases, but you can't forget that oxygen is O2, right? And here it's actually telling you that. And then we're still always going to use the grams to mole relationship. Okay, so here's what it gave us, right? The temperature just tells us which pressure to go find for the water vapor pressure. We don't actually use the number except to look up the value. We'll assume we're at sea level. And so, oh no, it told us 755. Ballpark, close to 1 atmosphere. We'll need the ideal gas law then. That'll get us to that number of moles, and then last the periodic table to get to the grams. Okay, first is going to the table. We're at 20 degrees. Subtract out that difference. Next, it wanted us to report the amount, but in mass. So the ideal gas law gets us to moles, and then last, the molar weight. So from the table, we get our corrected O2 partial pressure out of the total. The ideal gas law, our gas constant is in atmospheres. So we need to change into atmospheres. Right, then rearrange our gas law to solve for the amount of gas that's there. Now that's in moles. Got to have the atmospheres on, right? All of our units match up and cancel. Liters, Kelvin. Atmospheres or moles here is on the denominator of the denominator, and so that becomes the numerator. And then we multiply our number of moles times the correct molar mass, right? 32, 16 times 2, not just 16, because it's not an oxygen atom, it's an oxygen gas molecule. This isn't one where you can, take a guess at the value. I mean, we're near, 32 grams per mole, and it's kind of near STP, and that's 22.4 liters. So, this seems reasonable, but you can't really make a guess at it. It could have been a 0.5 gram or 3 grams or 5 grams. So, but this seems relatively reasonable. Okay, so the other portion of this, now we're combining back to the previous chapters, is before we used density or grams per mil, or the molarity. This is just our newest information about a reactant and or a product. So before we used density or molarity or just the grams to mole here. So it's the same procedure, but now it's using the ideal gas law combined with everything we did in chapter 4. And so this is one of the reasons that, depending on the book, it seems like this chapter on gases should be here right after chapters 3 and 4, where you handle chemical reactions in percent yield and limiting reagent. So gases usually they give it to you off the volume or the pressure instead of the moles, but we know that when we're figuring out percent yields or product, we need it in that mole to mole ratio, right? A to B just means generically, right, reactants to products. And so we use that ideal gas law to get us back and forth to the moles from whatever information that they give us, right? PV or T, we need to get to N, and then our moles to from our reactants to our products. If we're at STP, then this makes this a bit quicker, right? And STP, this relationship 1 mole to 22.4 liters, is just a special condition of the entire gas law, right? It's holding the temperature and the pressure constant, so you can look at just the moles and the volume. Okay, this example, we're clearly going to use the ideal gas law and basically do what we did in chapter 4, just using the ideal gas law, right? So it wants to know the volume of H2 of hydrogen gas needed to make 35.7 grams of methanol. And it tells us the pressure and the temperature this reaction is going to be run at. Okay, so here's what it gave us. This is what we're looking for. How are we going to get there? Well, you got to start with what they gave you, right? This time they gave us grams of the product. So we need to use periodic table to get to the moles, then our mole to mole ratio from the balanced equation, and then the ideal gas law to the volumes of the gas we're interested in. All right, if we're going, we're at this volume, this pressure here, but the ideal gas law, right, is in atmospheres, we'll need that conversion. The mass off the periodic table, then the mole to mole ratio 1:2 from the balanced equation. So first, get out of grams and into moles. Then our 2-to-1 relationship. Now we know how many moles. Rearrange the ideal gas law to solve for the thing we're interested in. In this case, it was the volume. So it was 32.04, so 37.5. So a little more than a mole, then it's in a 2-to-1, so a little more than 2 moles. Our units all cancel. We need to convert millimeters of mercury to atmospheres, since the ideal gas law are gas constants in atmospheres. Temperature needs to be in Kelvin. They gave it to us in Kelvin this time, a little less math. Our units all come from, Nick, I see. This is someone being dyslexic, 35.7 versus 37.5. Good catch. I don't know if the math was done wrong. I'd have to check it. But that's someone inverting these two. That was a good catch. But anyway, so that wouldn't change the number too much, right? If it was, inverted the 7 and the 3 or something. But so with that number of moles in place, plug and chug so the units cancel, and 66. Now, could you take a guess at this? It's an elevated temperature, so it's not really near the STP. You can see that it's over the mass of the methanol, and it's 2-to-1. So it seems about reasonable, but obviously, if it was a fill-in-the-blank type of problem, you'd have to calculate it all the way out to make sure. Okay, one more here. How many grams of water form when 1.24 liters of H2 reacts completely with O2? So oxygen and hydrogen, this is the modern day fuel cell, where only your product is water. This time we're at STP, so we're going to have a better shortcut. It wants to know how many grams form when 1.24 liters of hydrogen react. So the hydrogen and oxygen, hydrogen and water are both 2 coefficients in front, so it's a 1-to-1, an even relationship. The STP is 22.4 liters in 1 per mole. This is, about 1/20th of that, and water is 18 grams. So I would guess it's going to be around 1 gram, something like that. All right, but again, you find the fill in the blank to get the correct number. You got to do the work. So how are we going to get there? From it, the only information up here is the liters of hydrogen, so that's obviously where you got to start. We're at STP, so we have that shortcut, so we can use that relationship to get to moles. This isn't much of a conversion, since it's the same coefficient. Anything divided by itself is 1, so the moles actually stay the same there. And then we're going from the molar amount to the gram amount, so off the periodic table. So now you can see this is why that dimensional analysis we covered in the beginning in chapters 2 and 3, and then applied it to chemical reactions in 4 is important. Right, our liters of hydrogen cancel, then moles of hydrogen, then moles of water. And look at that, it was pretty close to just what I guessed, about a gram. And it makes sense when you see the 1-to-1 doesn't change it. So really it's just dividing by 22.4 and multiplying by 18. Okay, this next portion here has a touch bit of math, but really it's more about conceptually thinking about gases and reviewing the things we covered, taking a step back from all the math. So the way to think about gases is like bumper cars or a demolition derby. They expand in every direction, except those are limited by gravity, 2 dimensions, so they go in all 3 dimensions. Nothing stops them. That take the shape of the container. You've seen at some point on TV or wherever a clown make balloon animals, right? You've blown a balloon up. You can squeeze rubber balls and things, and they take the shape whatever container they're in. You've blown a bubble, and we did the density, and it goes, underwater. It goes rising up to the surface. So the densities for solids and liquids was in grams per mil, where gases were grams per liter. So ballpark, gases are about 100 to 1,000 times less dense than solids or liquids, right? Like really light liquids and solids were below water, right? Things float on water. But heavier metals and things were around 20, between 10 and 20 grams per mil. Gases, it depends on the gas, from hydrogen to is the lightest to something that's almost a liquid. Right, they're compressible. That kind of goes with the shape of the container. We did, pistons going up and down the internal combustion. There's an ideal gas law, which means you can treat the gases all the same regardless of what they are. So they're homogeneous, right? They're mixed throughout the solution, the mixture. And we didn't see this too much or talk about it or see too many examples, but fluid, I mean, you can blow gases, right? You've blown out a candle on a birthday cake or something. They move. All right, so everything we just talked about there, the scientific way of describing this is really kinetic molecular theory. And the density is really low, so that means there's a lot of empty space between the gas particles. And here again is sort of like they're showing you what this one gas molecule does inside this box, right? This is sort of the cartoon, its path. The average kinetic energy of the particles is directly proportional to the temperature. We already saw this really, right? This is how a hot air balloon works. And we saw that temperature and volume were directly related. As one, temperature went up, the gas expanded, the volume went up. The new part here in this kinetic molecular theory is that not all the particles are moving at the same speed. And we'll come back to that. All right, so indefinite shape and indefinite volume. That's, a clown with the balloon animals. The gas molecules have enough kinetic energy to overcome the attractions, and you'll deal with that in Chem 162, why certain things are liquids and solids versus a gas. And they keep moving in all directions and fill up the container, however you have them contained, right? And every time you open a soda bottle, you do the opposite, right? When you open a soda bottle, you hear that sound, that psh sound, and that's the gas escaping. All right, our classic pistons, the guy who designed, wrote the book, must be a big fan of the internal combustion engine. We saw this relationship, right? As the volume goes down, the pressure goes up, because the pressure is a function of how many collisions the gas molecules have with the container, the edges, the sides of the container. The density was really low, right? This is due to the great distance in between, and why we can have an ideal gas law. Is that the molecules, unlike solids and liquids, spend very little time in contact with one another. The important part here is that they're moving really fast. And so even though they do collide with one another, it's kind of like you're playing pool, but in 3 dimensions. Except they don't lose any speed when they collide with one another. This density and pressure, this is just our numbers of moles related to pressure. Right, so the picture above has less molecules in there, so a smaller N, and thus a smaller pressure, right? The pressure is derived from the collisions with the walls of the container. So when you have more molecules, you have more collisions, you have a higher pressure. And also tying into our density, right, is an amount of something per volume. We already covered Boyle's law. You don't need to know the names, right? This is that inverse. We saw this already, right? The volume decreases, the pressure goes up. Charles' law was the temperature, right? And this is a better example than the cartoon one that was in the slides earlier, because there's the liquid nitrogen. And, this isn't exactly perfect because it's the rubber of the balloon, but still, it shows the point of it shrinking. It's much better in person, obviously, but how does this work? The speed of the molecules drops, causing them to hit the wall of the container less, and right, the flexibleness of the rubber balloon. We see less pressure because there's less speed and less collisions pushing the rubber balloon out. Avogadro's was the number of molecules. We kind of saw that one in the beaker with the 2 amounts of there and increasing the pressure, right? And the same thing here with a balloon. Each breath you take in and blow into the balloon, you add more moles. And so the volume increases with the number of moles. Same thing here with the partial pressures, except now looking at it in the kinetic molecular idea. Again, the interactions are small, the molecules are moving fast, the collisions you can basically ignore. And then we get to what we care about is the kinetic energy, the speed of these. Right? Molecules are not sticking together, that's the collisions. We'll see that coming up in Chem 162. And then one of the ways they make nuclear weapons is by gas diffusion. And that means how the gases move in relative to their speed by their mass, because they do, like, in order to make a nuclear power plant, nuclear energy, you have to have specific isotopes and sometimes separate them. And here they're just talking about, right, what volume is it's an area, and then a distance, and how much that changes is what we're getting to, right? The atoms are constantly moving. We can ignore the attraction between them. They don't stick, they keep on bouncing. And so we combine all these things, right? Pressure was the force divided by the area. If you think about it in a sense of the force is from one collision times the number of collisions. And then that, that was shown on that one square is the number of collisions over some given time period over that area. Then the mass is important, right? Think about if you were to get in a car accident, or you see those when they crash test cars, right? If you were going to get in a car accident and you could pick which car you're going to crash into, would you rather crash into a motorcycle or a bus? The motorcycle will do more damage, right? Because there's less momentum. So that has to do with the mass, right? The bus is heavy, has larger mass. So the force is a function clearly of the size, but also the speed that it's moving. And we know the speed's related to the temperature, right? And that's what we see down here. So all of this basically built up to our ideal gas law. Okay, once again, not a history class, so you won't be tested on who's accredited with this distribution. We make these analogies like we saw with the limiting reagent, where think of it as a accident on a freeway, right? And on a freeway, all the cars are basically going the same speed, little differences. But when you have large numbers of things, and remember the Avogadro's number, you have a huge number of atoms. So in a gas, you have a large number of particles, and there's this distribution, and it behaves what's called Boltzmann's distribution. He's attributed with discovering it. But what we actually talk about is the average of what all the molecules are doing. And since we know this is due to that mass, we'll tie it into the mass, and depending on how much math you've had, you'll see what's called RMS, or the root mean square. And here's what this Boltzmann distribution looks like. So you typically see this when someone in a large class writes a good exam, where the average is in the middle and the distribution is nice and round like this. A lot of things behave in this Boltzmann distribution. You could potentially see it quite often if you stay in science. Okay, and depending on if you've had physics, you might have seen this equation before. Right, our average kinetic energy of the gas molecules depends on the average mass and velocity. So again, average mass, if it's a mixture of gases, because they all behave the same and the ideal gas law applies to all of them. If you just have a pure gas, then that mass would obviously be, a single number. Gases in the same container have the same temperature, thus the same kinetic energy. So if they have different masses, the only way for them to have the same kinetic energy is to have different average velocities, right? So if you have a mixture of gases, let's just say two, right? If they're at the same temperature, that means their KE is the same. Thus, if their masses are different, then the V must be different. Sort of like this is pretty similar to the dilution equation, M1 V1 equals M2 V2, except it's 1/2 M and V is squared. So what it means then is the lighter gases are going to have a faster speed than the heavier ones. So here's that Boltzmann distribution for different gases. They're all picked at the same temperature. It's that same Boltzmann. It's just depending on the scale and the blow up of how you look at it. So in order to have that same kinetic energy, right, our heavier molecules have to move slower and the lighter ones have to move faster, right? So hydrogen is the lightest, 2 grams per mole, helium's 4, water's 18, nitrogen's 28, oxygen's 32. So the red for oxygen is really the same as the hydrogen. It just depends on the scale, right? You've all zoomed in on a picture or screen or something before. So it's the same curve distribution. It's just the units and the increments are different, right? So when you put them together like this, they look quite a bit different. Okay, will I put one of these on there? I think hold on, let me just. Yeah, I'm not going to put one of these root mean squared ones on there. I think we've got enough stuff to cover. Anyway, this is how nuclear chemists separate these isotopes. So if you've read and heard on the news about uranium ever, there's 2 main isotopes of uranium. There's 238 and 235. Isotopes of elements are exactly the same chemically. The only thing that's different is the mass. And so you can separate them here by these methods where the mass is different. MM here is the molar mass. It's a little too much physics up here at the top, so we'll lightly cover it, but I won't put one of these on the exam. The important more take away home thing here is that what we care about is here's the hot air balloon, right? Your gas at, well, this would be an ice, but at a cool temperature has a much lower average velocity, right, is speed. Then you pull the chain on a torch, it heats up the air, and the speed is moving faster, and thus it expands, and you have more collisions, and it takes up a greater volume. So the air inside the hot air balloon heats up, and that makes the velocity faster, which gives it that volume and makes it less dense. So we'll cover this one here, but I'm not going to put one of these on our exam. It feels a little much for us. If you're a math major, engineering, you'll see, I'm sure, root mean squared again. This one wants us to find the velocity for O2 at this temperature. We want 230 Kelvin, so add 273 to it. This has to do with the molar mass, so grams per mole. It's really just kind of a plug and chug, right? Our gas constant, and then it's just the temperature and the molar mass of your gas. The reason I don't think I'm not going to put this on a test, we don't need to focus on it too much, is you won't really care or need the speed of the molecules again, unless you're going to go into some sort of engineering that overlaps with it. You won't see this again the rest of the year, the rest of this semester, or in Chem 162. You can clearly see here in red, right, the mean free path. This, again, you kind of already could tell from the cartoonish view over here is like it's showing you what this molecule did, right? And you've seen cartoons where they have the street behind them that tell you where they're moving. Again, it's sort of like bumper cars or a demolition derby. They're moving in straight lines until they collide with something else, either another molecule or the wall of the container, whatever it's in. And so this distance that it travels between these collisions is called the mean free path. Diffusion and effusion are the processes that separate these. So it's the collection of molecules spreading out from some high concentration to a low one, is diffusion. So when you take a big breath in and you exhale, that's basically diffusion, right? You have a higher concentration in your lungs and you're compressing your diaphragm and your rib cage, and that forces it out. Conversely, the collection of molecules where it escapes through a small hole into a vacuum is called effusion. Both these rates are calculated and come from the RMS via the average velocity. So this is getting to how they separate these gases. So for gases at the same temperature, it means that the rate of the gas moving is inversely proportional to the root mean squared of that molar mass, basically combining the two, right? Here's the rate that the gas is moving, and everything else stays the same in the equation, which is kind of why we didn't need to focus on the last one terribly. And it really comes down to that mass. So here's a picture of what this effusion looks like. And this is a really expensive process to do for nuclear energy. And one of the reasons poor countries don't have nuclear energy is it's incredibly expensive to undertake. So you have a temperature difference and then a small hole here, and the gas molecules escape through it into a lower pressure, a vacuum. Again, as usual, it's not a history class, so you don't need to know people's names, but Graham is accredited with discovering this. And if you have two different gases at the same temperature, then the ratio of their rates is given by the relationship of their mass, right? We saw in the previous one that the rate was equal to the square root, and that comes from the 1/2 mv squared. And so the rate of one is equal to the rate of the other by comparing those masses, the square root of them, of course. So this seems a bit more straightforward math and is relative. So I'll put one of these on the test. The problem will be really similar to this example. Calculate the normal mass of a gas that diffuses at a rate of 4.62 times nitrogen. Okay, so what that's saying is you have some gas over that you don't know over the gas of nitrogen, and it's 0.462, or 46% of the nitrogen rate, right? So what do we know? We know the two relative values. We know the mass of nitrogen, and so you can rearrange and solve for the mass of the unknown gas. And since it was lower, right, 0.46, that must mean that the gas is heavier. So what would have a mass of 131? You would go to the periodic table, and you could find, whatever gas is on there, and our periodic table is color-coded with what things are gases. This mass is a little bit high, so it must be, well, this one didn't tell you what temperature, so it could be hot and take something that's normally a liquid and it could be a gas or something. Like this seems kind of like close to bromine or something. Chlorine is 35 and it's Cl2, that'd be two of them, that'd be 70 something. So this is even a little low for that, but maybe one of those noble gases is close to this argon or xenon or something. All right, so all chapter long, everything was tied into the ideal gas, that gas law. But what's the difference between how gases really behave? So real gases don't always behave like the ideal gas law. And when do they do this? They do it at high pressure or low temperature. So the ideal gas law, the reason it works is it assumes no interactions and no attractions between the gas molecules. And it assumes the gas molecules don't take up any space. Basically what this means is low density and that the molecules are moving fast. And if the molecules are moving fast, the temperature is fairly high. All right, so when is a gas not a gas? Well, at low temperatures, it cools down and becomes a liquid. And then at high pressures, that's when the concentration goes up and the molecules get incredibly close to one another. And so at low temperatures and high pressures is when a gas starts to become a liquid. So an ideal gas law obviously won't work as the gas approaches the liquid phase. So at high pressure, the amount of space occupied by the molecules starts to compete and be important, and you can't just ignore it, right? So some things in mathematics and calculations you can ignore because their contribution is so small. But as the pressure of a gas gets higher and higher, the molecules get closer together, and you can't ignore that space anymore. If you've ever filled up a propane tank, you've experienced this. So if a propane tank for cooking in a barbecue, if you've filled it when it's empty, it's fairly light. You go to the hardware store or the gas station, and when they fill it up for you, if you shake it, you can hear liquid sloshing around in there. Same thing with a lighter. If you're a smoker, you'll see a little bit of liquid in there. And when you push down on the tap without hitting the sparker, you can hear the gas coming out. So that works, or the reason it behaves like that for those gases is because they're already at room temperature and pressure close to being a liquid. The molecular volume makes the real volume larger than the ideal gas law would predict. Van der Waals is something we'll cover in Chem 162. This is just introducing it. But basically what van der Waals is it's the collisions. Right, so van der Waals modified the ideal gas law equation to account for the molecular volume. This is this correction factor. And it's different for every gas because of their different sizes and shapes. So what we get here with this is we get a correction factor for the ideal gas law. This is beyond the scope of our class. This won't be on the exam. It's a bit too much for us. The point of it is, here in the picture you see a red and a green, and notice here the pressures, these are incredibly high. So a soda bottle is something like 2 or 3 atmospheres. It's way down here, right? And 1 atmosphere is, these increments are 200 in atmospheres, 400, etc. So anything below 200, and 200 is really, that's an incredibly high pressure. You need like a metal cylinder, or like, this is the kind of pressure that happens in a black hole and things like this. So we'll never experience, even in a chemical plant, you can't reach these types of pressures. Because the real molecules take up space, the molar volume of a real gas is larger than predicted by the ideal gas law at high pressures. And so here we see this deviation from the ideal gas, and they used argon here. And you can see it starts to fail and deviate away from the ideal gas law, the PV equals nRT. But this is beyond anything that we'll ever do, and even chemical engineers aren't going to operate above this. So as far as the pressure goes, it doesn't have an effect for anything we care about. All right, so that's pressure, but what about temperature? So at low temperature, our kinetic molecular theory, the gas molecules are moving much slower. So now when they do have collisions, they're going to spend more time near each other, and the attractions between them, which you'll cover in the beginning of 162, like how the attractions work and what they are, they start to become important. Those interactions and attractions between the molecules make the real pressure less than the ideal gas law would predict. Right? Van der Waals is, it's a name again, it's not a history class. And we saw that constant. Here's another correction for it. Last one was B, this one's A, and it's just another correction factor beyond the scope of our class. But here's what we see. Right, so here's again our pressure, and then the temperature. So we see that if the temperature's pretty low, right, and room temperature is 270 something or close to 300 is in here in the middle. Now this is doing xenon, but you can see as the temperature goes up, the gases behave closer to ideal. And it's only at really low temperature and or really high pressure that the ideal gas law fails us. So here's the full combined equation for the ideal gas law with these correction factors in there. Again, well beyond the scope of our class. There won't be one of these on here. None of you will ever see this or use it again, so we don't need to focus on. What this is just going through is, for most things, all year long in freshman chemistry here, you're doing y equals mx plus b straight line plots of things, quite a bit more in Chem 162. So here it's showing you this plot. Whenever you're plotting two things, you're trying to get a straight line so that you can show its usefulness. And then here they picked out a few gases, right, and where these things deviate away. And notice they all come back down here and meet, right, and the ideal gas law stays at 1, but these things behave differently. And in Chem 162, we'll talk about these different gases and why some of this might be due to their structure, behavior, and things going on. But these pressures here are insane, right? So a soda bottle and then is like 3 atmospheres, and we live at 1 atmosphere. So everything we're dealing with is way, way down here where they almost all converge, right? Obviously, we're not at 0, but these pressures out here are quite large. Okay, it's not a geology or atmospheric chemistry class, so this isn't, the details which aren't important, but the whole point of learning chemistry is to look at molecules and how they behave, and so this actually has a better overlap for all of us, because we live here on Earth and we breathe gases. And we'll see a bit of chemistry and things going on. And what the red line here is the temperature. So over here on the left is the altitude. Right, you can see Mount Everest, and if you've been up in the mountains or gone on a plane, right, it gets colder the higher you go up. And then it sort of levels off, and the reason it shoots back up here is we've got chemical reactions going on in this stratosphere. This is the ozone. And so the ozone absorbs UV light, right? You've been outside, especially in Hawaii, right? Somewhere where it's warm, you've gotten a sunburn, you can feel the sun on your skin, and it's breaking bonds, and breaking bonds takes energy, and those bonds are in you, and you feel it, and there's a warming effect. The same thing happens to ozone up here in the stratosphere, right? Once those reactions, and the ozone tapers off, and so there's nothing going on here in the mesosphere, and so we see the same cooling effect that we see down here. at near sea level. And then up here is where higher nuclear type of reactions happen with the outer atmosphere, and why the space shuttle and re-entering orbit from the moon and whatnot, you need serious materials on the spacecraft in order to survive these things. Okay, air pollution is materials that are added to the atmosphere that wouldn't be present in the air without, basically, we say us, right, humans. Pollutants add into the troposphere, that's the lower atmosphere where we live. And the reason this is important is there's a direct contact with us. And especially, if you're over there on the Big Island, you've heard, the VOG. And you feel this in your mucous membrane. So that's your lungs, your eyes, your mouth, your nose. There is pollution that adds to the stratosphere, and that's the CFCs, and that's stuff that's used in refrigeration. Those chlorofluorocarbons is what that stands for. And they work their way up into that ozone layer, which takes a long time. And since there's no weather up there, there's no mixing. Those chemicals don't get, washed out, literally rained out. All right, let's talk about what some of these things are. So sulfur can come from lots of places. The Big Island, right? The volcanoes, that. It's irritating because it can react with your eyes. So it's combustion because there's heat. The other place sulfur comes from is coal. And not that we don't have any coal power plants, but as you move to places that do, which the eastern part of the United States, Northeast, has some, this creates acid rain. So as the sulfur combines with oxygen via heat, whether it's the heat from a volcano or a power plant where they burn the coal, you make SO2. SO2 can then react with more oxygen and make SO3. And then either of these combining with water, you can get to sulfuric acid. And then when it rains, the acid combines with the water, and that's what acid rain is, one portion of it. This also happens with nitrogen. So nitrogen and oxygen are mixed together in the air we breathe. So anytime there is enough energy via, whether it's a lighter, a campfire, any car, anything that's burning anything, any lightning strike or forest fire, you have nitrogen and oxygen reacting, and it does the same thing where it makes that element, this time N, and makes NO and NO2. NO2 we saw, you see this when you fly into the classic cities or Mexico City or LA in the summertime. You'll see sort of a brown haze in these type of cities. Same thing, it irritates your mucous membrane, so your lungs, your nose and throat and eyes. We haven't covered what an oxidizer is. Briefly in chapter 4, we looked at it, but you'll cover it in Chem 162. And once again, the equations, just the coefficients are a little different, but basically it's your NO, and a lot of times they call it NOx, because it doesn't matter whether it's NO just 1 or 2, because it just combines with oxygen and water, which is in the air, and then you get nitric acid, right? And again, a contributor to acid rain. Another pollutant is CO. And so anything that is burning and has more incomplete combustion, which means the ratios aren't right. So if you ever are in a car that's up in high elevation, or you see black smoke coming out of any type of truck or anything like that, the mixture, the ratio, there's not enough oxygen. That's your limiting reagent. And so the gasoline isn't being completely burned, right? So if it was completely burned properly in the right ratios, you should get carbon dioxide and water. And both of those are colorless, right? There's CO2, carbon dioxide in your breath when you breathe out, and you don't see any color to it. Same thing with moisture, right? One of the reasons we drink water is, and especially when you're working out, running, you're taking bigger, deeper breaths, and that same collection of gases of bubbling water, bubbling air, collecting it through water, there's that partial pressure from the water vapor. So every time you take a breath, you're losing some moisture. So in vehicles that have any carbon-based fuel being burned and they don't have enough oxygen, you don't go all the way to CO2 and you get CO. So CO, unfortunately for us and other oxygen-breathing animals, O2 and CO are very similar, and the CO actually sticks to your blood stronger than O2. So it doesn't take much CO because it sticks stronger to the blood for someone to die from it. So you can't get O2 if there's CO. Apparently it's not like choking to death. It's more like you just fall asleep. You know, that's what this says down here. You get like a stupor and unconsciousness. And then, if you stay near the CO spot source, you can die. Ozone is also a pollutant, which you wouldn't think of because you hear about the ozone layer protecting us from the UV light, but in which it does, but we want it high up in the atmosphere. So we haven't gotten to redox chemistry. You'll get to it in Chem 162. But hydrogen peroxide, we saw that formula, it's H2O2. Right, and ozone is O3 versus oxygen is O2. Both hydrogen peroxide and ozone have an extra oxygen atom. So they operate very similar, right? And you've put hydrogen peroxide on a cut and it hurts, right? So ozone, it gets produced by electrically, so lightning storms. And then it has some other, can be generated in smog by complex chemical reactions. And this is one of the reasons it's also a lung and eye irritant, which means mucous membranes. Sometimes if you're around a photocopier making lots of copies, right? You've seen a photocopier or printers, there's electrical energy in there, and it can generate some ozone. But again, it's similar to hydrogen peroxide, and you wouldn't squirt hydrogen peroxide in your eye, right? Or breathe in a mist of it. Maybe you've gargled hydrogen peroxide if you've had a really bad strep throat or something like that to kill the bacteria in your throat. Ozone is the same principle chemically, except the hydrogen peroxide you can control the liquid. This is a gas, so there's no way to really get rid of it. Any of these type of pollutants, and that's why you stay indoors. You can, if you're outside, it's a gas. There's no way to really hide from it. So that sounds sort of doomsday-ish here, and that's why this table here is just showing you that historically humans became aware of this in this sort of the late 60s and throughout the 70s, and then implemented catalytic converters and all different types of things to try and improve this. And you can see this is slightly outdated, right? 2004. I don't know what the change is since then. And it's difficult to lower these things because our population is expanding. And this comes from things like the Clean Air Act and whatnot. But again, it's not a history class, so. Oops. So how does that ozone work? We saw that temperature increase up there in the stratosphere, and this is the reason that they say sunscreen or skin cancer and sunburns and sunlight exposure are worse and getting worse than they used to be, is that ozone layer absorbs this UV light. So as there's less ozone miles up in the stratosphere, more of this UV light is making it down to us at sea level. And so what it does is that ozone gets hit by the light and it breaks apart into an oxygen molecule and a free oxygen atom. Now this reaction quickly goes back, but it doesn't involve UV light in the reverse. So it absorbs the light, splits apart, comes back together, and absorbs the light again. And that's the absorption of this is why we see that temperature increase. The same as when UV light hits your arm or your skin and you can feel it warming you. So these gases that are great for refrigeration have chlorine, fluorine on carbon, and so they're called chlorofluorocarbons, or CFCs for short. And gases like you've seen, a balloon pop, when they're used in refrigeration, it's difficult, to contain them all. And once the gas escapes, there's no way to get it back. And so it escapes, and these things are very non-reactive, which is why they're good for compression and air conditioning uses. But then they don't react because these carbon, fluorine and carbon chlorine bonds are really strong. So they exist and slowly rise, kind of like the way a helium or a hydrogen balloon would. And slowly they make their way up and they get to higher and higher levels of UV light. And then that UV light can break the bond just like it did for ozone, but now it does for the carbon-chlorine bond, because the carbon-chlorine bond is weaker than the carbon-fluorine bond. And then unfortunately for us, what that does is these chlorine atoms that get spit out, they can decompose the ozone, right? So the chlorine atom reacts with the ozone, generates this ClO and O2. If you've got that ozone around absorbing the UV light, it can generate another O atom. The O atom combines with the ClO, spits out O2 and Cl. And so what you get, if you look on the product side, is you get 3 moles of O2, 2 moles of O3, and an oxygen atom on each side, right? And the chlorine atom on each side. So they cancel each other out. And so what it does is it decomposes that O3. Whenever you're observing atmospheric reactions and things of this nature, this is the South Pole. You can observe things that have to do with sunlight or the lack thereof by viewing them at the poles, because you get extremes of 24 hours of daylight or darkness. And so this is just showing you that, it gets exaggerated, this effect. And so these are, over several decades. I mean, it says 3 decades, but right, 79 to 91 is really only 22 years. But the Nobel Prize was awarded to a chemist where I went to grad school for this. I think he's passed away since then, but this was, in the 70s and then 80s. And this is what's attributed to increases, and I'm sure everyone probably has someone in their family that's gotten skin cancer. And this is affecting us all globally. Okay, so we finished there a little early. We've got a little bit of time, but I don't want to jump off and start a new chapter. I hope this was a little more interesting with real-world applications of pollution and some chemical reactions that explain things. And I'm talking about ozone a little bit more instead of the first half of the chapter is just straight ideal gas law and solve for the unknown and math. I'll have to think about what question I would put in here, but you could just skim through it. I don't know that there'll be a question on the test from in here. it'd be tough to come up with something since you could just come back straight to it and Google the answer. But I hope this part made class a bit more interesting for the day. And so, yeah, I'm not going to move on and start the next chapter. So I know that means we'll finish a couple minutes early, but I hit the unmute. So this is the time for questions, comments, thoughts, feelings, etc.
Yeah, I have questions again.
Cool.
If you scroll back up, the rate of the gas, like the formula for it, before the effusion part. Yes, at that part.
This one.
Yes. What is that symbol?
Oh, okay. So this symbol here, well, it's an italicized A that is called alpha, but it also, this symbol means proportional to.
Okay.
So what proportional to means is that it's not an equal sign that says, 2 plus 2 definitely equals 4. But what it does mean is, like, if you have two positive numbers and you're adding them together, the number's going to be bigger, right? So it's like the volume and the temperature are proportional to one another, right? As the temperature goes up in a gas that expands, the volume goes up. It's not saying the exact values that are equal to one another. So this is a good question. This is a combination of here where it's actually equal to one another. They're saying, this root mean squared, and it's the gas constant T and the mass, etc. But this is only important if you're going to do like specific temperatures and a specific gas, and you want to use the gas constant and whatnot. So notice the equation looks the same. What it's saying is if you had two gases that are in the same container, then their RMS is the same, and that's really just the rate. And so you could compare to, right? The rate is if the rate increases, then this has to increase as well. They're proportional to one another.
Okay, I thought you needed that to solve for something.
Well, so that's why in the example here, since they're proportional and we're not looking at the rest of those constants, we're just looking at the comparison between the two, then you can compare them directly now. So this is just leaving out all the details from this equation, right? Because it's the same. If they're in the same container, it's the same gas constant, it's the same temperature, it's the same 3. You don't need those in there.
Okay.
Yeah, so if the rate, really what it comes, all those things are really constants. And so what it comes down to is the rate is a function of the mass. Then if you're looking at two gases that are in the same container, then if one's moving faster, the mass must be different.
Okay. And you were saying kinetic energy along with, you said like car crashes and stuff. There
Yeah,
was a
well,
separate thing
the
for it.
the 1/2 mv squared it'll look similar if you've been in a physics class to momentum,
Yes.
right? And so
Uh,
imagine you're driving, I don't know, a Toyota Tacoma or whatever, and you get to pick what you get in a car crash with, right? What determines the how bad the accident is the mass of the thing you hit and the speed of the thing you hit, right? A motorcycle that's going the same speed, let's say they're going the same speed. So if they're going the same speed, that's similar to what's on the screen now. If they're going the same speed, then all that matters is the mass of the thing that you hit. So if you're in your Tacoma, you hit another Tacoma, it's even, right? But if you hit a motorcycle, there's very little mass. If you hit a bus, it's much larger, right? So
yes.
that's what this is doing here, is saying the rate is essentially the speed, and then the mass is the mass, right? So, you know, would you rather get into a car collision? Like, it could be the same, a motorcycle and a bus, if the motorcycle's going, I don't know, 300 or 400 miles an hour, right? And the bus is only going 30, because that makes up for the difference in the mass. Let me go back to, right, that's this here, right? The O2 would be the bus, and the hydrogen would be the motorcycle.
Okay. I
Right.
thought I saw like another variation of the kinetic energy within the moving molecules.
So if they're at the same temperature, which is what this is trying to say, right? So this one's saying everything here is the same temperature. And so that means that they all have the same kinetic energy, but they're not all the same mass, which is, the kinetic energy is the same thing as the momentum.
Okay, so if you need to find, you said that kinetic energy is directly proportional to the Kelvin temperature. So you could find the actual temperature just by using the half mv squared, correct?
Yeah, like here, like you know, in theory, if you had every other value in here, you could find the temperature. True. But usually the way that we find the temperature of things is with a thermometer. We don't do ridiculous, difficult, you know, measurements in order to find T. But yeah, you know, in all these problems. So like in the normal ideal gas law, you could be looking for PV, or N or T. But usually for temperature, you just use a thermometer, right? You're not calculating it, unless you're doing chemical engineering, some kind of engineering where you want to know at what temperature something will happen for you. But for the most part, you know, we use a thermometer to find the temperature, and then you figure out the rest of these things that are of interest.
All right.
But what'll be on the test will be something like this, where I say, hey, they're at the same temperature, which means their 1/2 mv squared is the same. And then, you know, I give you, where was that problem? Maybe something like this, right? And that's where this equation comes from, right? They're at the same temperature, which means their rate is their speed is the same. That's V, and the differences in their masses.
Okay, and
And
then you would try to find the molar mass of one of the gases then.
yeah, and so, you know, like this one, you don't really need to know the actual speed. It's just telling you the relative rates. And
Okay then.
so like, let's say this same one is on the test, and I'm like, which is the most likely gas? Like hydrogen, which is, its mass is 2 grams per mole, you know, or I say oxygen, but oxygen's 32, so this one's 28. It's way too close. And then, you know, I don't know, xenon or argon or whatever's 131, or none of the above. So you wouldn't even need to actually solve it. You could be like, oh, hydrogen's way too light, right? These two rates are different, so the masses have to be different. So is it really light like hydrogen, or is it heavier? Because it's not going to be the same molecule, or nearly the same, right? Nitrogen and oxygen have nearly the same mass.
All right then. I think that's all I have for now. Have a good one.
Okay, cool. Bye.
You too. Have a good day.
Sounds good.